Here you see this early on in the course, I started you with that collision lab, and we did 3 or 4 different small steps paying attention to various changes. And one of the changes that or the things that we eventually got to was that there was a connection in that the ratio of masses ended up being the opposite or inversely related to the change in speeds. All right, we developed that showed up in our analyses. And in fact, this ends up giving you the uh, conservation of momentum. Okay, we have the momentum of um, mass 1 and its change in speed. That's mass times speed is always a momentum, and a mass times a change in speed would be the change in momentum, is the opposite of this other one. And all we have to do is bring in the time equivalence, that the time of this collision is the same in both cases. All right, and so the rate of that change with time is constant to both. And of course, this really is just m1a1 equals the minus of m2a2, which really means force 1 is minus force 2. So the conservation of momentum rule ends up giving us Newton's third law, that forces are equal and opposite. They always come in pairs, equal in magnitude, opposite in direction. So that's just a quick review of that. What I want to do now is prove to you that something else is true. And I want you to look at these 2 pictures here are before and after collisions. Here we have the before collision, and here's the after collision. And you have a better color for that. You have these momentums that you can look at. So in those spots right there, underneath each one, it gives you momentum. So let's look at momentum 1. The final momentum, P1, was a -1. Initial momentum, P1 initial, if you will, was 1. So the change in that momentum would be -1 minus 1, or -2. The second object, all right, it had a final momentum of 1, an initial momentum for that object of -1, and so the change in momentum for object 2 would be 1 minus a -1. Well, that just equals a +2. So if I were to sum the momentums, so change in momentum 1 plus change in momentum 2, I'm going to get a -2 plus a 2, or 0. And what that means is change in momentum, the sum of the changes in momentum in a system, are 0. Now, it wouldn't matter how big or small either object was, how fast or slow they are, uh, short of non-conservative force losses like friction or whatever. I'll always conserve momentum. And it doesn't matter what the collision objects are. And so It's again, it's this reciprocity idea or Newton's third law. You know, the bug on the windshield problem, it's hard to believe that the bug hits the car as hard as the car hits the bug because the car is so much bigger and faster. But the bottom line is the mass speed exchange is conserved in these collisions, all right? It, in systems where there's not some other way for that to escape, all right? But in general, momentum's always conserved. It goes somewhere. So think of a car crash. Uh, some of that momentum, most of that momentum goes into crunching the cars. Some of that momentum is translated to noise. So the noise travels through the air at the speed of sound, and that sort of leaves the car-to-car system. But it's momentum that went somewhere. So the momentum's conserved. Also, that's usually not an elastic collision. They stick together often or eventually break apart. But in this simple situation that we're paying attention to, we get uh, change in momentum one plus change in momentum two. If we could have 100 of these balls clanging together, and all the momentum changes would add up to zero. Now, if it starts going in 2 dimensions or even 3 dimensions, it gets harder because then you got a cosine of this and a sine of that. You got all the parts to pay attention to. Somebody move. There we go. Thank you. It's lights always going off on us. So conservation of momentum, that thing right there. So let's bust this out a little bit more. It equals zero. Well, let's write these. So this is going to be momentum one minus the initial momentum for object one. And then change of momentum two will be the final momentum of object two minus its initial momentum. So P1 sub zero, P2 sub zero for the initials, and those all equal zero. Well, we can put this into a balance, much like our energy balances that we saw. And so I'll have the final momentums. They easily, you can see right here, a P1 plus a P2. Those work out a piece of cake. And that the other two are negative, and they're going to go to the other side and just turn into a sum of the initials. And so we would normally write it, the initials on the left, the finals on the right. We'd write them that way. So you have initial momentum over here, and the final momentum over here. So that would be our momentum balance. That's basically the same way we do our energy balances. And to be more explicit, this will turn into M1 speed 1 initial plus M2 speed 2 initial equals M1 speed 1 final plus M2 speed 2 final. So this would sort of be our expanded version of the conservation idea, conservation of the change of momentum. And fun for the whole family will be had by solving for each one of the speeds. Okay? So I'm going to write one of those out. So we would have, if we take M1, V1 initial, so I got to rewrite it since I changed screens here. You don't have to, unless you absolutely want to. So if I solve one of these for V1 initial, all right, so I'm going to solve for that one. So I'll have M1 V1 initial will equal M1 V1 plus M2 V2 minus M1 V1 initial, which means the initial speed of object 1 would be equal to mass 1, speed 1. I'm going to go ahead and move this other part that's compatible with it right next to it. So all of that over mass 1. Well, this works out kind of nice because M1, what we need to see is that this right here is just a change in speed 1. The V1 and the V1 initial parts that have the common factor of mass 1 is just the change in speed. So I have M1 times change in speed 1 plus M2 V2 over this M1. Well, let's take a look here. So V1 initial would just be the change in V1 plus M2 V2. There is a mistake in this. This right here I can't subtract away the thing that I was solving for. That needed to be M2. I was that was what was supposed to be coming over here. So we need to go back. I hope you weren't writing in pen. You should never write in pen. These need to be mass 2. All right. Going to erase this. Glad I caught that before publishing. So V1 initial will equal M1 V1 plus M2 V2 minus M2 V2 naught over M1. So if you look right here, this, whoops, I wanted to highlight, not erase. This right here, that part of the fraction is just going to drop out to be a speed 1. So if you were to write it out explicitly, you'd have M1 V1 over M1 plus this other part will be mass 2, and this is where you have just change in speed 2. The V2 minus V2 naught, where they have the common factor, is just delta V2. So delta V2 right here. And these M1s cancel. And V1 initial ends up being V1 final plus the mass 2 mass 1 ratio times delta V2. And really what you have here, if we were to take this speed 1 and bring it over here, we just get the negative of the change in speed. All right. A V1 naught minus initial speed minus a final speed is a negative change, because normally the change is the final minus initial. But if I have the initial minus final, that's a negative delta. And so I get back exactly what we had in the other one. So I'm going to add a screen here. So since I'm running out of room, I'm going to rewrite exactly what we have on that screen. So V1 initial equals final speed plus mass 2 over mass 1 times a change in speed 2. Well, if I subtract V1 initial minus V1, what I really have here is a negative change in speed 1 equals the mass ratio change in speed 2. This is just the momentum, impulse momentum theorem that we developed earlier, because if I bring mass 1 over here, negative mass 1 times change in speed 1 equals mass 2 times change in speed 2, which means the negative change in momentum 1 equals the change in momentum 2, which means if I add the change in momentum to both sides, change in momentum 1, I get change in momentum 1 plus change in momentum 2 equals 0. I get back exactly what we had, which is unsurprising given where it came from. So what good is this? Well, this right here, this equation, is a way, if I know all of the other parts of the puzzle, if I know the final speed of object 1 and I know the change in speed of the other object and the masses, well, then I can figure out what the initial speed would have been. And of course, I could solve it for any of the other 3 speeds. The final, I could turn it around and the final speed would be the initial minus the rest of that equation. I could collapse it down to delta V1 and expand V2 and get the other 2. And it's really just going to be a handful of equations that have the same basic structure based on what you're solving for. So here's what they would look like if I were to write all 4 equations. I would have the one we just did, V1 initial would be the final plus the mass ratio 2 to 1 and the change in speed, or I could solve that for V1 and have V1 initial minus that very same thing. I could have V2 initial. It's going to have the same structure, except the mass ratio has to flip. And the reason for that comes from our prior work with the collision lab. We found that there was an inverse relationship between the masses and the change in speed. If you remember, what we had noticed during that lab was that if you had 2 balls collide that were unequal masses, you notice that every time after the collision, the smaller mass obtained a greater speed than the larger mass. And so that's that inverse relationship, is that the mass is inversely proportional to the change in speed. Smaller masses, bigger change in speed; larger masses, smaller change in speed after across that collision. So that's why we noticed previously, before getting to this unit, is that if you have a ratio of mass 1 to mass 2, that's going to be equal to the opposite of the change in speed 2 to change in speed 1. That's what you mean by inverse relationship. If mass 1 goes up, and then its change in speed goes down. That's why its change in speed is in the denominator on the right-hand side and flipped around the other. So all of this really just boils down to this. It's the math side of what we did already. Okay, so we have that going for us. So what I want to do now is tie this into conservation of energy with some more exciting math that you can hardly stand the wait, I'm sure. we also know that energy is conserved. So we could write uh, kinetic energy balance, the change in kinetic energy initially, or just the initial kinetic energy equals the final kinetic energy. We could just keep it simple that way. And so if I have two objects colliding, meaning they have a speed, that means there's going to be a kinetic energy associated with each object before the collision and a kinetic energy associated with the object after collision. And if energy is conserved, then it's going to have the same features. So I'll have, and if you remember, hope you remember, kinetic energy is 1/2 mv squared, generally speaking. So that means that initially I'd have mass 1 plus the initial speed squared, 1/2 of that, plus 1/2 of mass 2 and its initial speed squared. And that would have to equal the final speed squared versions, mass 2 and mass 1 and their speed squared. Well, the half is common throughout, so I can drop it. m1 v1 naught squared plus m2 v2 naught squared equals m1 v1 squared plus m2 v2 squared. Well, that's the uh, conservation of kinetic energy. And notice conservation of momentum looks almost the same. The difference being squareds. Every one of the speeds is squared in the kinetic in the energy part, but not in the momentum part. And ultimately, there's a lot of ways to understand energy, and energy is an easy concept to mess up because we like to think of it as stuff. It's always about stuff, and it's moving or potential to move, but it's not actually a substance. Speed squared is another way to characterize the essence of energy. You've all heard of Einstein's famous equation, E equals mc squared, and that's the speed of light squared. And so speed squared is a huge issue in energy. In fact, Newton and Leibniz, Newton invented calculus. Leibniz thought he did too, and others think that Leibniz might have found it first. If it hadn't been for Newton, Leibniz most certainly would have done it. He was a pretty smart guy, and he was working on it as well, for sure. But most scholars agree that Newton done it first. All right, but they argued about energy, and Newton was probably wrong about energy not being squared. Well, if he meant the same thing, he was fixated on momentum, and I think he might have been just thinking about momentum instead of energy. But ultimately, uh, speed squared won the day in terms of energy, and but they're tightly connected. So I think in one sense you can sort of see where the historical uh, spat might have um, come into play. So that's pretty much the uh, long and short of just what kind of pulling momentum and energy together. All right. So now I want to do a few problems uh, related to these two ideas. So let's So this problem, an 80 kilogram astronaut drifting in space outside of a space station or something, got a wrench, 2 kilogram wrench, big wrench, 4.4 pound wrench. How fast a throw will give this astronaut a 20 centimeter per second recoil? All right, so just think about it floating in space. You were just floating there. Unless you're already moving, or if you're at rest completely, then you'll just sit there. But if you exert a force to throw something and change your mass, so you have a astronaut and wrench system that's 82 kilograms. The astronaut obviously exerts a force in throwing it and gives that 2 kilogram wrench some speed. And so just like you've seen in the movies, and if you were to watch this actually happening, you would see the wrench start moving in that direction and the astronaut going in the other direction, right? And if you've seen the space movies, they're trying to get back to the Mars movie where he's about to miss his ride back, all that stuff. So how do we go about this? So we would just simply set up a momentum balance. So we'd have the mass of the astronaut and the speed of the astronaut. That would have to end up equaling the mass of the wrench and the speed of the wrench. If momentum's conserved, that's what we would have. And so this is pretty simple. The speed of the wrench is what I want to know. And that's going to give me the mass of the astronaut, speed of the astronaut, over the mass of the wrench. Well, if the mass of the astronaut's 80, and the speed of recoil that I want is 20 centimeters per second, well, that's going to be 0.2 meters per second. And the mass of the wrench is 2 kilograms. And so the kilograms drop out, and the speed of the wrench that I'll get in the end here will just be 80 over 80 times 0.1, and so that's 8 meters per second. So the astronaut needs to throw it at 8 meters per second. Maybe they practice these things. I don't know. They know just how much to wind up to get whatever. But it really wouldn't matter. Throw at something, and you're going to get a recoil speed. And 20 centimeters a second, that isn't that fast, but it's fast enough. You look at a meter stick, it's about, I don't know, just a little bit longer than my hand. My hand's 15, 18 centimeters. So if you have long fingers, you might have a 20 centimeter. So doing that once a second, that's decent. You won't run into the space station too hard and poke your suit or anything like that. So we have that. A ball that has a 300-gram mass. It's moving horizontal, so it's kind of our ball in the box problem. 14 meters a second, hits a wall, bounces back at 10 meters a second. This is typically what happens. Things don't bounce as high as if we drop them from a height. They're not going to bounce back up to that height. If we throw it at a wall, it's not going to bounce off the wall any harder than it hit. We always lose something in an interaction like that. Some of that momentum goes to the wall, vibrating it, heating it up, deforming it. Eventually the wall will have a dent if you keep throwing something at it long enough, especially if it's a hard ball. But it's a soft one. It'd take a long time to do this. So what's the impulse? And so we haven't given a lot of attention to the impulse, okay? because we've been paying attention to momentum. And so the impulse momentum theorem basically is you have delta P equals, I'm going to write it the other way. You have force delta T equals the change in momentum, and we call this the impulse, the force delta T. Okay, so this is where we get the impulse momentum theorem, is that force time component equals the delta P, or change in momentum component. Both of these really boil down to mass times change in speed. Okay, all this really is, you just think of F delta T. This is ma delta T, and A delta T is delta V. And of course, momentum is just m delta V. So the impulse momentum theorem is just a rearrangement of the thing we've already done a few times now, the conservation of momentum idea. All right, but it's a way to think differently. I have a time-dependent left-hand side and a change in speed dependent right-hand side. It's just a different way to characterize the problem. And ultimately, this thing right here, it tells me that force is delta P per delta T, which is an m delta V per delta T, which is just an ma. So Newton talked about force this way. I don't think he ever wrote ma, but it is effectively true. So that's just a little bit of background for what we mean by the impulse. Okay, so strangely enough, the obvious letter choice for impulse. Anybody want to take a swing at this? No, that would make sense. Capital I? That would make sense, except we use that for current in second semester. So, since I is more important and taken for other things, J. J is impulse. Okay. Again, I just work here. I'm not responsible for picking these letters. So F delta T, we call it the impulse. All right, so it's going to be this weird kind of units thing. And so we can solve directly for impulse. So impulse will be change in momentum, which is going to be mass times the change in speed. The ball has a mass of 300 kilograms, which would be 300 grams, which would be 0.3 kilograms. The change in speed was going to be, what is it? A negative, let me go back here. Went too far. So let's be a little bit more careful here. So we're going to have our P final minus P initial. Let's write this down. So the impulse will have a mass that's obviously not changing and a speed, its final speed, minus mass times the initial speed. This problem is really important because we need this to take note of directions and therefore signs. So when we start to develop the ideal gas law from a momentum perspective, which is the essence of kinetic theory, which is our main topic and one of the topics in this unit, we have to pay attention to the speed. So doing this a little bit more explicitly helps us not make a sign error All right. So I'm going to have mass times speed minus speed initial. So let's put this 0.3 kilogram mass in here. And then the final speed. Well, the final speed, okay, is going to be which way? It's 10 meters per second is what it bounces off the wall, all right? And so if I throw it at the wall, if I throw it right, throw it in a positive direction, okay, when it rebounds, it's going a negative direction, all right? So that means I have a negative 10 meters per second, and then minus, okay, since we're doing a change in momentum here, the initial speed of 14 meters per second, all right? So 0.3 kilograms times a minus 24 meters per second. So yes, somebody was doing that. And so 0.3 times 24 is 7.2. And this is a weird unit to deal with, kilogram meters per second. So those would be momentum units or impulse units. And we may just want to know the magnitude, so to have the impulse to deliver to the ball is 7.2 kilogram meters per second. So an impulse would be kind of like what you feel. So like if you belly flop into a swimming pool, you're going to feel some impulse initially when that water is finished changing your speed. All right. And so if it was not from a very high height, the slap on your belly won't be so dramatic. But if it was from the roof of the house, then you'll notice that much more because the time, the amount of force in that time interval will be significant. So that gives us the impulse. Sometimes we want to know just what the speed is. Sometimes we want to know what the impulse is. Various systems. Anybody watch Star Trek? I was total Trekkie, still am. But this would apply to any of the space fictions about going at or near light speed or the jump to insane speed. On Star Trek, they actually have a manual. Pause this. So this situation we have, wooden block sitting on a table. So we could draw a picture. All right. And a bullet. Coming at it at some speed greater than 0. It lodges itself in the block somehow, because bullets are kind of capable of doing that sort of thing. And then it gets the whole block moving. All right. And it goes, the block goes some distance, x, before friction brings it to a stop. So there's a momentum way to look at this, and there's an energy way to look at this. And the importance here is that I need the momentum part in order to obtain the speed that I would use in the energy thing where I'll consider friction. So it would be difficult to do this by forces, especially with the information provided, but using momentum and energy in this way will help us. And so what we can do right off the bat is pay attention to the momentum part of this puzzle. So we'll do our momentum analysis. So I'll have the mass of the bullet. So we have, we'll use mass of wood, or MW, for the um, uh, block, since bullet and block have the same letter. So the mass of the bullet, the speed of the bullet, plus the mass of the wood, uh, well, I guess the bullet initially, and the speed of the wood initially, will have to equal, and when the block and the bullet come together, I'll have mass of bullet plus the mass of the wood, and then that'll be uh, uh, a new speed. Um, we'll just call it um, S for the system, speed of the system. All right. Now, initially, that's zero because the block's just sitting there. So that thing just drops out. And so if I want to know the speed of the system, okay, we're using V sub S for speed of system, it's pretty easy. I'm just going to divide both sides by the sum of these two masses. And so the speed of the system, the combined system, will just be whatever the bullet momentum was initially divided by the combined mass of the bullet and the block. All right. So literally, I guess another way to look at this is I just have the initial speed of the bullet, because that's the only thing that was moving. It embeds itself in uh, something else, and so now the mass of the bullet as a factor is reduced because I'm dividing it by its mass. That would give it a 1-to-1 speed if it was just its own mass, and it would be pointless. But now that I'm dividing the mass of the bullet by something bigger than the mass of the bullet, now I have this, I'm really going to be, because a bullet is going to be much lighter, okay, than, say, this block of wood, or these two blocks of wood that we're seeing, that no one on video can see, all right? So a bullet's much less massive than this block, but it has a lot of energy, a lot of momentum with it. So it'll get this thing moving if it stays in, whether it stays in it or not, it'll get it moving, even if it goes through it, all right? So that means the speed of the system, bullet block system, is going to be some fraction of the speed of the bullet. That should make sense, because when you stop and try to make sense of the situation. So we have our statement. This will be what the speed of the combined system is. So that's one piece of the puzzle. Now we can do the energy part, all right? So energy, and let's do after collision. So this is right after the bullet embeds itself in the block and imparts speed to the block. So the kinetic energy, K sub S, meaning of the system, we're just using S for system. We could have done BW for bullet wood. Really wouldn't matter in this case. That's going to be just our standard 1/2 of the mass, or mass of the system, M sub S. And since it's on a table, we'll assume it's horizontal. We'll just say that this is going to be, uh, uh, we could call it x, or we'll just do vs squared here, right? So 1/2 mass of the system, which was mb plus m wood times the speed squared. And so that's going to be what we just solved for, mb initial speed over mb plus mw, all of that squared. Hopefully you see that this system mass will kill that system mass, but I have to make sure I square the numerator, okay? Well, let me be more careful here. I'll write this out. What I should do is it'll kill this square as long as I square those two. So I'm going to end up having one of those things left over in the denominator of my thing here. So I'm going to have mass of the bullet squared, initial speed of the bullet squared, over 2 times mass of the bullet plus mass of the wood, or the block in this case. So our kinetic energy of the system after collision will be what I just wrote. So I'll kind of put it over here again. You don't have to write that. I'm just, since there was a long line of stuff there. That's just one piece of the energy puzzle. So what we need to remember is that we have this work equals change in kinetic energy business. So we have the change in kinetic energy. It went from, well, it's going to start at this initial kinetic energy, the K sub S, K of the system, right after the collision. And then its kinetic energy is going to change. It's going to go to 0 because friction will do work. There will be a force of friction exerted over the distance that friction does work, bringing this initial kinetic energy of some amount, slowing it down until it stops. So we have work done by friction, and we've seen this before. So let's be clear here. The work is going to be friction work. The change of kinetic energy is going to be with respect to the system. So I'm going to add those subscripts in there. The S subscript is what we just worked on. And in fact, it's really just going to be, well, it's going to be the negative of it ultimately, since it's going 0 minus our Ks here. So work done by friction. Well, that's easy. That's basically the friction force. We usually use lowercase f for friction, and that's going to be mu times the normal force, which we typically don't write as a capital. We write it as a lowercase. All right, so work done by friction is going to be that force times the distance. Okay, force times distance. Work is always going to be a force times a distance. And since this force is the force of friction, it's going to be mu n times that distance. Has to equal our Ks, basically. All right. So the work done by friction be that force of friction times n. Force of friction is going to be mu, and since it's moving, it's mu sub k. You might remember that in the reading. We have mu sub s for static friction. when it's not moving, trying to get it to move, and mu sub k for kinetic friction when it's actually moving. And the normal force will be mg, all right? But our mass is a weird mass. It's a sum of masses. So it's the mass of the block, or mass of the bullet plus the mass of the wood, or the block of wood, times g, okay? So mu n equals the total mass times gravity. And the work done by friction includes this distance that it goes, d, and so we would have to put that in here. So that's the work done by friction. And that has to equal the kinetic energy thing that we just solved for. All right? So if I want to know the distance that it travels, okay, I am going to have to solve for d by dividing away all of this stuff, mu k mb plus mw g, and I have to divide all of that stuff by this ks business that we just wrote. And that would give me my distance will equal the bullet's mass squared, initial speed of the bullet squared, all of that over a big long mess of our 2 mu k g times the total mass of our system, but it's going to get squared because I'm dividing what was already there again. So I'm going to have that total mass thing squared. So that's a lot of ciphering. And again, it just gives us a general formula about this kind of collision. So this classical bullet in a block business requires this approach. Okay, this is the most efficient way to solve this kind of problem where you have what's called an inelastic collision, meaning the objects stick together. Two speeds, one of them might be zero, but one of them needs to not be zero, and they need to collide. And if they stick together by any means, so sometimes cars will stick together after collision, sometimes they don't. Sometimes the bullet will stick in the block and make it move. Sometimes the bullet will go through the block and still make it move. It's not likely that the bullet would go through the block and not cause it to slide unless it's glued to the table somehow, all right? So there's a lot going on there. You'll find the same sort of analysis in your book. Every physics textbook always has this kind of problem in it. And it's the important thing here is seeing the connection. Is a conservation of momentum, okay? The momentum has to be conserved, but the energy situation could be a non-conservative energy situation, namely a transfer of energy out of the system of the bullet and the block by means of friction. So we conserve momentum, but we may not conserve energy in the system because the system was the bullet and the block. And so the bullet and the block, by means of a exchange of momentum, a change in momentum, okay, of an inelastic collision, imparted a certain amount of kinetic energy to a block. That block system, the bullet block system, is in contact with a surface, a frictioned surface. And that surface, which is not part of the bullet block system, changed the kinetic energy. So ultimately, energy period, energy in the universe is conserved. But friction forces are what we call non-conservative forces because frictioning will dissipate energy out of a system like the bullet block system to the surroundings. So the surroundings get a net increase in energy and the system loses some energy. Energy is still conserved, just not in the system anymore. It went somewhere else. And so the law of conservation of energy still holds in that the sum total of energy in the universe doesn't change. But depending on what system I'm paying attention to, yes and no. Okay. Uh, Biological application, real quick, would be protein folding. Anybody heard of that? Kind of important. You take amino acids and they fold in space, and we sort of halfway understand why. Still have some questions about that. Um, but if you don't fold those amino acids up, you don't get no proteins. You don't get no proteins. You don't get no life. Okay. And so it is what's called an entropically driven process, meaning entropy, which is ultimately heat dissipating over time, spreading throughout the universe. Um, uh, Protein folding actually depends on. In fact, all living systems are entropically driven. You need heat. You need heat energy coming from somewhere to fuel um, these other things. So uh, pregnancy is entropically driven. All right, pregnant people, they can get kind of hot, especially if you mess with them. They get real hot. Okay, and you don't want to do that. But there's a lot going on in gestation. It's an entropically driven process. Something's got to be giving up some energy. A lot of heat energy going on in that, all the way down to the protein folding. All right. So, anyways, pretty much went out of my pay grade there since that's a bunch of biology stuff. But I'm at least mostly right. I know that much. But you could look up, and it gets complicated. Those of you that go into biology, you go deeper in the pool of thermodynamics, and there's Gibbs free energy, enthalpy. There's it. There's a lot of ways to track all of that. All right, and entropy is just part of the puzzle. There's other ways to describe how those heat energies are pushed around in the process of building proteins, molecules, etc. All right, so physical chemistry. Some of you will take that kind of course and tie it in with the biology and whatnot. All right.